started, so we'll start that button. And you all here, I can submit that button. And that means we gotta stop the music button. That's okay. Good morning, everyone. I'm so glad you're here, except you're not here, you're online, so I can take that off. There we go. A little less muffled there. Oh, what are we doing? We're doing some very simple stuff. This is Algebra 2. We are in the middle of a new type of function, right? So last week we had the test. That was great. Finished that. And you took a look via, what's the thing called? Desmos marble slides at exponential functions. Exponential functions are awesome. They get slowly, and there's all they just like take off. And you've probably heard the expression, oh my gosh, it's growing exponentially, right? It's taking off, it's going really fast. That's usually what they refer to. When they say growing exponentially, they're not talking about the negative part, right? Where it's the reverse. Your graph would look like this, right? So here's my y-axis, right? They're not talking about this part where it's almost flat. They're talking about this part over here where it's almost vertical. But not actually vertical. We've seen vertical asymptotes. It doesn't have that, only a horizontal asymptote. And what we're going to do this week is we're going to take a look at the flip side, the reciprocal. What happens if you want to un-exponential? Then what do you call it? Turns out they gave it the name logarithm. I'm not entirely sure why, but we'll explore that a bit today. Right, so here we have, I'm going to do a real quick summary of 10.1 and then we'll focus more of our attention on 10.2 for the logarithms, right? So here's the bit that you read about, did the notes, and we didn't have a day to talk about, but you've done enough with exponents by now that there's really not that much new going on here, except that now the variable is the thing in the exponent, okay? The independent variable is in the exponent. Y equals some a times b to the x. So now these a's and b's serve a very important, distinct purpose. A is being multiplied in front of the whole thing. This is your scale factor, just like it is with every other function. I could also, if I wanted to, we could add on, plus c, and that would shift the whole thing up or down, right, just like it does with any other function. And you got to explore this with the marble slide. The most important number here, though, is b. And in this case, it's actually aptly identified as b for the base. Okay? B is the base, x is the exponent. So it kind of works out phonetically there. All right? And you can have exponential functions either grow and get bigger and bigger and bigger from left to right, or decay from left to right. They shrink down, smaller and smaller and smaller, but never quite zero, right? There's always that horizontal asymptote component to it. And look at the difference between a decay and a growth. What do you notice about their bases? Their b that's being raised to the x. Okay? That's right. For growth, b has to be something bigger. Okay? Exponents mean, and at least one interpretation of an exponent means repeated multiplication. Okay? I'm going to take whatever I start with, whatever a is. If it's not there, remember it's an invisible 1. I'm going to multiply it by b how many times? X times. So as x increases, I'm multiplying by b again and again and again and again. If b is more than 1, I'm multiplying and I'm getting bigger. I'm growing. If b is a fraction, less than 1, but still more than 0, then we have decay, because you're multiplying it by a fraction. You're saying, hey, take half of this, and now take half of it again. And now take half again, right? It gets smaller and smaller as you go. Please notice that the base must still be greater than 0. A negative number to an exponent is not an exponential function. B cannot be negative at all, because then you get this flippy-floppy thing. Look what happens, right? Anything to the 0 power is positive 1, and then negative 2 is just negative 2, but negative 2 squared is now positive 4. Multiply by negative 2 again, you get back to negative 8, and so it does this flip up and down. Bazonker's thing. Put it into Desmos, see what it looks like. It is pretty cool, but it is not a well-behaving function whatsoever. At least not as we would like to define it. Okay. So dealing with exponentials most of the time is fairly straightforward. Remember when I said don't just memorize your multiplication table, you ought to know your cubes and squares at this point, and powers of 2. That's going to be huge here, right? Powers of 2. 2 to the what power is 2 squared? Like it's literally written here. You just need to match those exponents. If the bases are the same, the exponents must be the same. And I think I have, right? That's, in fact, your goal. If they're not, make it as such. Okay, look at this one. 3 to the x equals 9. Well, 9 is 3 squared. And so now if I can rewrite 9 as something with a base of 3 so that the bases match, if the bases are the same, the exponents must be the same. So x must be equal to 2, right? Same thing here. If the bases are the same, well, my base over here is 3. This is an 81. 81 is 3 to the 4th. Ah, now I've matched my base 3 and 3, so x plus 1 is equal to 4. Solve that mini algebra 1. This is like pre-algebra equation. Come on, solve that for x. It must be 3, right? To solve exponential equations, rewrite as powers of the same base, get both sides to have the same base, and then you can set each exponent equal to each other and solve for x from there. You can even work that out with fractions here. This is tricksy. Okay, 4 to the 2x equals 1/4 to the x plus 1. Power rules, 1 over x is just x to the minus 1. Okay? So 1/4 is 4 to the negative 1. And now we have power of a power, okay? Exponent, thing with an exponent raised to an exponent, you multiply the powers. So this would be 4 to the negative x minus 1, right? Negative 1 times the whole binomial x plus 1. So distribute that negative to both pieces, both terms, and then you'll be left with just a base of 4, base of 4. Oh, 2x equals negative x minus 1, solve for x. This is about as tricksy as it gets when it comes to exponents. They got all the tricks up their sleeves right there. So with that said, are there any questions on exponential functions? No? Okay. This operation works great if you can rewrite this thing as the same base. What if you can't? What if like hypothetically we had some crazy, okay, 4 to the 2x equals 1/5 to the x plus 1. How the heck are you going to write 1/5 as a power of 4? That's ridiculous, right? This is not, at least not anything I would know off the top of, a multiplication table. It's got to be some crazy, weird, negative fractional thing. It might not even be rational. I don't know. Okay? How the heck are we going to solve this? How can we undo exponential? How can we get that variable out of the exponent without relying on this kind of a trick? Enter logarithm. Okay? The logarithm is the inverse of exponential. It is the reverse operation. It is what you will use to undo exponents. And I've heard, I have no idea if this is actually true, but it's one of those around the rumorville, what do you call it? Heretically? No, I don't know. Might be heresy, but I've heard that the name logarithm comes from the phrase a logical way to do arithmetic. Log Logarithm. It's a portmanteau of I don't know. Okay? Logarithm, logical arithmetic. But it's really handy. Like I said, it literally undoes the exponent. It's the inverse operation, which means your exponential equation flipped over the y equals x line. This is now your log function. This is what it looks like. And instead of the horizontal asymptote here, log now has a vertical asymptote at x equals 0. Strictly speaking, in a formal manner, the log function, log with base b of x, is defined as, right, the value y such that b to the y equals x, so long as b is not equal to 1. Okay? So notice we still have in our exponential form b to the y equals x. B is our base. And in log, b is the same but a base. Okay? So you're always, always, always matching bases. And so base to the exponent gives you a number. Log of that number gives you back what was the exponent. The reverse. Okay? I like to say that the log undoes exponentiation. Or better yet, it answers the question, because this is how it's always presented. Here's an equation, and you ask yourself, what is the exponent, or what was the exponent that gave us that number? Log operation will tell you that. Its answer reveals what was the exponent. Okay. Now, this has some really practical applications, and our textbook did a wonderful job presenting that probably the most common right from the beginning. Logs are really good for compressing numbers together, particularly if you have large numbers and small numbers. Okay? Think about this right here. The actual relative intensity of sound. How much louder is a jet engine compared to a noisy kitchen? Okay, if you got the blender going, what? I can't hear you, I'm making a smoothie, versus the jet engine taking off in the nearby airport. Look at that, the relative intensity there. You have 10 to the 10th versus 10 to the 12th. That's a huge number, right? 1 followed by 10 zeros. That's a lot. 6 zeros is a million. 9 zeros would be a billion. This is 10 billion loud. This is 12 zeros. This is a trillion loud. So how much more noisy is the jet engine than the noisy kitchen, right? It is actually 2 more zeros worth, right? 10 zeros versus 12 zeros. It's 100 times louder. Right? Compare that down to the whisper. A jet engine is 10 to the 12th relative loudness. Your whisper is only 10 to the 2nd. Subtract the exponents. 12 minus 2 is 10. The difference is 10 to the 10th. The difference is 10 million. No, that'd be 7. 10 billion. A jet engine is 10 billion times louder than a whisper. Okay? It's freaking ridiculous. The scale that we're dealing with here. You can't plot this on a single sheet of paper because you try to be reasonably like, okay, I need the pin drop, barely audible, a whisper, normal conversation. You divide your paper into 1,000,000 increments from 0 to 10 to the 6th. Okay? You can't fit the jet engine on there because you would literally need 1,000 more sheets of paper. You with me here? Comprehend that scale. It's hard for your brain to understand. This is as many times bigger than this as this is than that. How do we deal with this? How can we possibly graph all this stuff plotted onto a single graph so you can see it all together? How did they fit it on here? You're supposed to have equal spacing between, hash marks on your number line. They didn't do that here. This is not the same amount between here and here as it is between there and there. It's a log scale, a logarithmic scale. What they've done is they've taken the log of the relative loudness. Okay? And we've given that a unit, that's a special name now called decibels, or decibels. Deci for 10, because notice we don't just have the exponent here. Okay, the log takes the exponent. Log of 10 squared log base 10 of 10 squared is 2. But we don't have 2 right there. We have 2 times 10. Right? That's the decibel part. 10 times as many. So we at least have a little bit of range. Okay? Now we can see, oh, look at this. Normal conversation is 60 decibels. A whisper is 20 decibels. Does that mean normal conversation is only 3 times louder? No. It's a power of 3 louder. Okay? The decibel tells you how many powers louder it is. The jet engine, 120 decibels, will literally break your eardrums, is not 6 times, right? 20 times 6, 2 times 6, 12, keep the power of 10. It's not 6 times louder. Remember, it's 10 to the 6th louder. It's 1,000,000 times louder. Okay? Understand the difference there. What the log scale lets us do is it crunches all those big numbers so that we can spread them out. Now on here, from 0 to 20, 20 to 40, right? Add 20 on each tick mark. Now these are evenly spaced. Okay? The log scale is evenly spaced now. The real scale, right, goes insane, right? It grows exponentially. There's that term again. All right. Any conceptual questions at this point? No? Okay, so let's do a few examples together, and then I will turn you over to the quizzes for the day. All right, so first up, writing in log form versus exponential form. Notice that these are complete statements, right? They are finished equations, no variable, no missing, no unknown, nothing. It's just one of them is written as something to an exponent, and another version is written with a log. There is no exponents shown here. Okay? You can freely convert from one to the other. Let's go blue. 5 to the 4th power equals 625. Keep the base the same. So instead we can have log. The base was 5, so we'll put a little subscript 5 under our log. Of what? Of the argument. Log always reveals the exponent. So if you can't remember what goes here, at least remember log should always equal the exponent. This is how I process it in my mind. I remember log equals exponent. So the 4 has to go there. I used the 5, I used the 4. The only number left, it must be 625 of there. If you ever wanted to know, hey, what power of 5 is 625? You could ask your friend who has memorized the powers of 5, or you can ask log and say like, hey log, old buddy, old pal, log base 5 of 625 is what? It's 4. 5 to the 4 is 625. Ah, you can go back and forth there. Okay? Our negative exponents doesn't make a difference. Log of base is 7. Log of the answer, what was the answer, I guess, the 1 over 49, equals the exponent negative 2. We can go the other way. Log base 3 of 81 equals 4. So that means our base is 3. Our exponent is 4 equals 81. 3 times 3 is 9. 3 times another 3 is another 9. 9 times 9 is 81. Yeah, that works out. Okay. Same thing here. Log of base 36 of 6. So our base is 36. The log is equal to 1/2, so our exponent is 1/2. 36 to the 1/2 power. We know 1/2 power is the same as square root. The square root of 36 is 6. So we can freely go back and forth from one to the other, okay? It's just like if we wrote a whole bunch of y equals x squared equations, and we converted them into x equals square roots of y equations. That's all we're doing, back and forth. Okay? Some circumstances you will want the exponent form. It'll be clearer what's going on, what number, you'll recognize it, or the operation later performed. Whatever context of greater problem you're dealing with, maybe this will be easier to use, maybe this will be easier. Okay. All right, next up, evaluate these ones. What is log base 4 of 256? Okay. This is where that what question is log asking. Log is asking 4 to what power is 256? 4 times 4 is 16 times 4 again, right? Well, 16 times 2 is 32, times 2 again would be 64. So 16 times 4 is 64. So we've had 4, 4, 4, it's at least 3. 64, I need at least 4 of them, right? To get to 200, 64 is almost 50. It's a little more than 50. 4 50s would be 200. It sounds like 4 64s could get us to 256. In fact, you'd be right. It is 4 to the 4th to get 256. Okay. How about this one? Log base 2 of 1/8. 2 to what power is 1/8? 2 times 2 is 4, times 2 is 8. That's 3. I need at least 3 involved there in somewhere. Except it's not of 8. It's of 1/8. I need a fraction. How do you turn a base into a fraction? You give it a negative exponent. -3 is our answer. Okay. Look at this one. This is a funny business. 3 to the power of log base 3 of 21. What the heck are we supposed to do with that? Don't panic, don't panic. Log base 3 of 21, right, is a number. Okay? And then we want to find 3 to that number. Get me so far? Well, we could rewrite this. If you don't know, 3 to what power is 21? 3 times 3 is 9. 9 times 3 is 27. I don't know, right? Wait a minute, it's not an integer. Shoot, what are we going to do? Well, we can rewrite this guy. Right? This is actually, right, saying 3 to the x equals 21. Okay. It's going to be whatever this exponent is, whatever this log base 3 of 21 is x. This will be equal to 3 to our x. But rewriting this log as an exponent tells us, hey, 3 to the x is 21. This whole thing it undoes itself, right? 3 to the exponent. But log undoes the exponent. It says, no, take your base back down to 21. Our final answer is 21. It's probably the most confusing part. A log inside of an exponent, as long as the bases are the same, log base 3, exponent's base 3. Log inside the exponent, it undoes itself right there and then. Okay. Take a look at this one. Same deal. Log base 5 of 5 to the -1. Log undoes the exponent. So as long as I have matching bases, the answer is just -1, right? Because log asks 5 to what power is 5 to the -1? What kind of question is that? You just said it right there. 5 to the -1. Done. Okay. And that brings us to our final rule here for solving log equations. Right? Just like exponential equations, if you have the same base, you can set the exponents now equal to each other. With logs, if you can find logs of the same base, you can set the arguments equal to each other. Right? So let's take a look at this. Log base 9 of x equals 3/2. Well, this is asking Log reveals the exponent. This is saying base 9 to the 3/2 equals x. So here all I had to do was rewrite it as an exponent, as an exponential equation, and now hey, that's answered equal to x. There we go. What is 9 to the 3/2? Well, 9 to the half power is 3. So that would be 3 to the third power. 3 times 3 is 9 times 3 again is 27. Right? This equals 3 cubed. Okay? Always try for the half power first, usually. Right? You want to make things smaller before you make them bigger again. It's usually easier to work with. Over here, same thing. What is our base? Our base is 1/10. Our exponent, log tells us the exponent, it must be -3, equals our argument here, x. Hey, we've got the variable by itself. All we had to do was switch format. So what is 10 to the -3? Well, the negative tells us flip it around, or more precisely, take 1 over that. 1 over 1/10 is 10. And now 10 cubed equals 10 times 10 times 10. Just 1 with 3 zeros. 1,000 equals x. And then here is the doozy. What to do when you have log on both sides? Oh, I can't just use my write it as an exponential trick. But I can still use what is actually the same property as the exponentials. If the bases are the same, that's the first thing you check for. Ooh, this is log base 5. Oh, please be log base 5 over here. Yes, oh, thank goodness it is. Now we can simplify it. Because if the logs are the same, technically what I'm doing, the operation I will perform, right? Back to good old algebra 1, just do the same thing to both sides. I can exponentiate both sides. I can say, hey, take some number, in this case, our base, 5, right? 5 to the power of all of this. And we'll do that on this side. We'll take 5 to the power of all of that. And remember what happened over here when we had 3 to the log base 3? We just get the argument. So 5 to the log base 5 is just 3x minus 1. Over here, 5 to the log base 5 is just 2x squared, right? So that's what allows us to say, as a general rule, if we have the same base logs on both sides, we can just rewrite the arguments are equal to each other, just like we did with the exponents. If you have the same base on both sides, write a new equation, the exponents are equal to each other. But this is technically the operation we perform to get that step. Now it's just a quadratic. You can solve that from there, right? We dealt with the tricky part. We dealt with the new bit. Any questions there? All right, now it is your turn. Please go to joinmyquiz.com. We've got 14 questions for you here today. I'll make sure I've got the right settings. One attempt here live. Here it is, joinmyquiz.com, game code 267905. As usual, a retake version will be posted at the end of classes today. But let's see what you're capable of as of now. Let's get some practice in right here. Show me what you can do. Fresh off the bat. Maybe this is easy for you. Some of these should be pretty easy. Six, that's all 5. Okay, everybody's here. Let's go. All right, that's a little loud. Turn that down. first correct answer. Off to a great start. Let's go there. We've got 15 minutes left. That's plenty of time to work through these. Anything else? Your worksheet assignment is posted on Google Classroom. When you're done with the quizzes, you can go on to the worksheet. And please send me any messages or emails if you get stuck or have any questions on anything. That will wrap it up for the YouTube stream, so we're going to end that here.